Okay, this is integrated to 1.3.4 notes, angles, and sides of a triangle. So we've gone through all of the relationships with the parallel lines and the transversals, but now we're going to actually use those to help us do some stuff with triangles. You'll take a look at the agenda today. There's a whole bunch of different eTool tutorials that I have linked, and it's because you're going to have 3 of them available to you today, which I highly recommend that you use. It's a good way to visualize what's happening. But some of them are pretty self-explanatory, others not so much. So the tutorials that I have for you, just in case you get stuck using them, the Desmos activity itself, no video is longer than maybe 1 minute. So we're going to go through this section of notes, and then next class period, we will only have 1 more set of notes for this chapter. And it's going to be very, very, very brief, just kind of as a review. So what we're going to do is we're going to go through and do some color coding here. So you take a look at the triangle up here that's given to us in the corner. And what we want to do is we want to find where that corner kind of exists throughout the entire shape. So in addition to the eTools here, there's a resource page that goes with this, which is also linked. I highly recommend that you have it and that you use it, kind of cut out the triangle and kind of tile it your way around so you know which ones to shade. Now in part B, we're also asked to go ahead and shade the other corners as well. So what I'm going to do is I'm going to go ahead and color code my little miniature triangle that I'm going to be using. So these are the colors that I am going to use. And then I highly recommend that you have 3 colors in front of you as well. Go ahead and pause this at this point and then come back and check and make sure that we have the exact same coloration. Okay, so I think I have all of my corners colored at this point. So I went through, I did part A, then part B as well. And then we're going to go ahead and use this as well on part C. Okay, so now on to part C, we want to take a look at this tiling and actually see if there's any type of relationship that's happening between these things. And there is. So I want to find a location where I can see all 3 colors next to each other. There's a whole bunch of them in here, but I think I'm going to hone in on this one kind of on the bottom. There's nothing else around it. So at this point, if I take a look at this, all 3 of those angles look like they're going to make a straight line. So I know that those 3 colors will make a straight line, which means that they're going to be supplementary to each other. If they're supplementary, then I know that they're going to add up to 180 degrees. So if those 3 colors next to each other create 180 degrees, then if I look inside a single triangle that has all 3 of those colors, so take a look over here at this corner right there, that triangle itself has all 3 colors in it as well. So we've already made the relationship that when you put all 3 colors together, you're going to get a straight line, which is 180 degrees. So now we know that all 3 colors inside the triangle are going to have to make 180 degrees. So we can now go ahead and finish up the statement up at the very top. So we want to know, let's see, if a polygon is a triangle, then the measure of its angles has a sum of 180 degrees. Okay, so now moving on to the next part, we do have this eTool that's popping up. It's going to be one of 3. So you can go ahead and kind of play around with this within the eTool, which I think would be a great time, would be right now. To go ahead and pause the video, go take a look at the eTool, kind of play with it or play around with it a little bit. Okay, now that you're back to this, now we can actually see some more relationships happening between these. So if we take a look at the picture itself, using the parallel line stuff that we've already learned, we know that angle D is going to be congruent to angle A because of alternate interior angles. That was one of the things we talked about last class. Then we also have the same relationship over here with angle E and angle C. They are also alternate interior angles. Now angle B is the question. So if we take a look up at the very top here, put a little box around those 3, you will see that if we take D and B and E and we add them all together, we get a straight line, which means those are going to be supplementary to each other. So let's go ahead and write that down. So if I take D plus B plus E, that's going to give me 180 degrees. And I know this because they make that straight line, so that these are going to be supplementary. But if you take a look back at the picture, because of the alternate interior business, I think we know that D and A are technically the same size. So I'm going to replace D with A. I'm going to drop down B, and then same rationale. We know that E and C were alternate interior angles. So now we can say that those are 180 degrees. So now if you look inside where we have the triangle, A and B and C are all within the triangle. So now we're going to get this 180 degrees for a triangle, which I'm sure you guys have been taught this before, but I don't know that anybody ever explained why. So our reasoning here, we'll go ahead and put in between, is that these are alternate interior angles. So that's the reason why we can replace the D and E. Now, whenever we have these three angles being added together inside of a triangle and we get 180 degrees, this is called triangle sum theorem. So you're talking about a triangle. It is the sum of the angles, and the shortened version for theorem is THM. So we have this other thing that we can now talk about. Okay, moving on to the next slide. So if we take a look at 1-105, we've already talked about the angles themselves. That's what we just did on the previous slides. This one is about the side lengths. So they gave us this sample triangle that has a 6 and an 8 on it. And I think one of the things I'm not too keen on with this question, but I get why they did it, is that they drew the picture for you. So once we typically see a picture of a triangle that has a 6 and an 8, a lot of people have a block and they think, oh yeah, okay, that's the only triangle that can be made. Well, I decided to draw two more triangles for you. And I went through and I measured these out before I even drew them and created them. The 8 lengths are 8 of the boxes that are on the graph paper that are on these slides, as the same as the 6. You'll notice that all 3 of these triangles look very different from each other, very different. I don't think that the 3 question marks are congruent to each other. So what you're going to do, again, this would be a perfect time to kind of take a break. You're going to go use the E tool for this question. Again, if you get stuck, take a look at the tutorial video that I posted as well, and just kind of play around with it and see if you can come up with some sort of a relationship that might be occurring between the side lengths. So as you're going through the tutorial, take a look, or going through the Desmos activity, take a look at the panels on the left-hand side and look at the lengths of the sides and how they're relating to each other. So moving on to the next question, or the next part of this. I think I did skip over maybe a couple of pieces of this. So let's go ahead and jump onto this part. So we have these. So you've gone ahead and you've played with the E tool. Hopefully we have a pretty good idea. So now we want to see, like, what relationship did we see? And there were a couple of ways that you could do this. The one way that normally sticks in my head is the fact that every side of a triangle must be smaller than the sum of the other 2 sides. So here, I'll show you what I mean. So on question number 1 here on part 1, I'm going to take every single one of those sides and I'm going to see if it is smaller than the sum of the other 2. And if it is, if all 3 sides are smaller than the sum of the other 2 sides, then you have a triangle. If it's not the case and they are equal to each other, it's not going to work, because you're going to end up with either that gap between the 2 lengths not coming close enough to meet each other, or you're going to have some crazy overlap. So the fact that they can't ever pull far enough apart from each other to create your triangle. So I look at this and go, 5 is less than 13. That's a true statement. Okay, then I'm going to do it with the other sides as well. So I'm just going to go one at a time. So 3 is less than 15. That's true. 10 is less than 8. Nope. This is not a triangle. So even if you were trying to do like a party trick and they were like, okay, here are the measurements. And you're like, okay, I can make a triangle, or you're trying to trick somebody into it. They can't. It's not possible. This one can't be done. So go ahead and take a moment. See if you can check 2, 3, and 4. Remember, every single side must be smaller than the sum of the other two. That's not the only way to do it, but that's the one that kind of sticks with me. Okay, so go ahead and double check yours against mine. 4 looks like it might be, but it doesn't satisfy the less than part. It satisfies an equal to part, and that's not going to work. So on this last part here, we want to come up with some sort of a relationship with them. So if it were me, I would go through and say that every side is smaller than the sum of the other two. But again, this is not the only way to do it. Okay, moving on to the next slide here. We're now at 106. So we've got this relationship now between the angles inside of a triangle. We know it's going to be 180 degrees if it's a triangle. We also know that for the side lengths, you have to have a special relationship between the sides themselves to even have a chance of creating a triangle. And then the third thing here, this really is the relationship between the size of an angle and the size of its corresponding side length. So if we go ahead and we take a look at part A. So part A has Maria going back to the figure over here that she has and starts talking about this opposite angle and opposite side. So I'm going to take a look back at the picture and I'm going to color code here what they're talking about. So they're basically saying that if you have this angle B here, and we want to think about the side that corresponds with it or that is its partner, we always think about the opposite side. So the side length that we would be matching with it would be the unit length of 9. Likewise, we would go through and we would take a look at the other ones as well. So this angle, so let's put the markers inside so it's a little bit easier. So I would say that this angle of 127, so angle B, is going to be corresponding or has a relationship with A and C. So if we go through and we take a look at this side length B to C, we're going to go to the opposite corner. So it's the only corner in the triangle that isn't actually touching that. So if this is side length BC, well, then B and C can't be involved. It has to be the other corner, which is going to be the 21. And we are going to talk more about some more detailed relationships between them later this year. Right now, we're just trying to see if we can come up with some sort of a size comparison type relationship. So if the blue line is side AB, then its partner angle, corresponding angle, if you want to think about it, cannot be A or B. It has to be the other angle, C. Okay, so what we want to do is we want to see if we can come up with some sort of a relationship between those. So we take a look at part A. What do we notice about the length of AC compared to the length of the other sides in ABC? Well, if you take a look at AC, it's longer. So I would say that AC is the longest side. So AC is the longest. Now, let's take a look at the angle. So its partner angle, which is going to be B. And let's see how that angle compares in size to the other angles inside. Well, it's also the biggest angle. So I would say that angle B is the largest angle. So I have that the largest angle and the largest side compare to each other, or they have a, if one of them is the largest than the other one, so its partner, its corresponding either side or angle is also going to be the biggest as well. So go ahead and play around with the E tool on part B. This was the one that I thought wasn't quite as user-friendly, so you definitely might want to take a look at the tutorial for that one. And then we want to see if we can come up with a conjecture about the relationship among the side lengths and the angle measures in the triangle. So go ahead and take a minute, play around with the E tool, come back, and then we can talk about part B. Okay, so moving on with this, hopefully at this point you have realized that the largest angle, its corresponding side is going to be the longest side. And it works the same way with the smallest angle and the shortest side, and the medium size angle and the medium length. So go ahead and write yourself a conjecture here. So for example, if AC is the longest side in a triangle, then its corresponding angle B is going to be the largest angle in that triangle. Okay, so moving on to C. So make sure that you have your conjecture written down for B. If triangle ABC has side lengths 4, 9, and 12 respectively, then which angle has the largest measure, the smallest? Use your tool to investigate and answer the questions. So what you can do is you can actually just mock up a little tiny triangle for yourself if you need a visual. So I think that's what I'm going to do. So I created a small sample triangle for myself, and I wanted to make sure that I drew it so that AB looked smaller and that BC looked twice as big, definitely bigger than AB, but that AC is hands down the longest side length here. So I think with the visual it might make it a little bit helpful. So if we take a look at this, we want to figure out what the largest angle measure is going to be. Well, we should actually just be able to figure out the largest side. So if we know that the largest side is going to be the 12, then I know for sure that the largest angle is going to be B, since they are partners with each other. So I would go ahead and write that down. So I know that the largest angle here is going to be angle B. Likewise, now I can go ahead and match the smallest with the smallest. So if the smallest one is 4, opposite that corner is going to be corner C. So I would say that angle C is going to be the smallest angle in this picture. And then go ahead and take a moment and see if you can figure out D. Okay, so hopefully you've played around with the E-tool a little bit. So at this point, I tried to mock up a triangle where 2 of the side lengths were going to both be 10, and then I have that third side length, which is going to be 12. I can make a triangle out of this because every single one of the sides is smaller than the sum of the other 2. Now, the being able to find the largest angle here, that one's not too bad. We know that the largest side is going to be 12, which means the largest angle is going to be angle B. The other one I feel like is kind of a tricky question. By saying, well, what is the smallest? I think it kind of leaves the impression that there's only going to be one of them, but that's not really the case here. Since both of those side lengths are the exact same measure, then we can say that their angles, so each of the angles are going to be the exact same measure as well. And then, well, what kind of a triangle is this? Whenever we have a triangle that has the exact same 2 sides being the same, we also have 2 of the angles going to be the same. This is an isosceles triangle. And hopefully that vocabulary word sounds familiar to you. I have a feeling that you guys talked about those. Man, I think that was a couple of years ago. Okay, so at this point, we're done with the book problems that kind of will help you out or lead you into the rest of the stuff that you're going to be doing today on the assignment. So here we've got our triangle sum theorem. This comes from the notes, and this is from page 7. This is the only thing that was left on page 7 that we still needed to do. So it was really just the idea, now that we've got our color coding that we did on the tiling pattern on the very first question, we can say that the sum of the 3 interior angles of the triangle are going to give us 180 degrees. And then we only have 2 more examples left on page 8 as well. I'm going to do part B first. So I want to show you something with part A because there's always more than one way to do things. We could even do part B a couple of different ways if we choose to, but I think the one that's probably the most straight to the point is being able to use triangle sum. So in this case, looks like we need a degree on the 117. All right, so what we're going to do is we're going to take these angles, we're going to add them all together. That's going to be 180 degrees. Our reason is going to be triangle sum. And then go ahead and solve this equation. So I think that's going to be 136 plus x. Subtract the 36 from the other side. And I think that's going to give us 44 degrees. So we have the three components that we've talked about so far. We have our justification or our reason. We have the correct equation set up. And then we have the work with the correct answer. Okay, moving back to A. One way that you can do this, and then we'll talk about this nice, pretty slick relationship, is if you take a look at the triangle itself, it's important to note that the x measurement is not inside the triangle. So you may have to do a little bit more work there. So I think what I'm going to do is I'm just going to come up with another variable. I can't call it x. I think I'm just going to call it y. So I'm going to solve for y first. So I know I'm going to use triangle sum because I'm going to add the 19 and the 23 and the y to get 180 degrees. Now, if I add those two together, that's going to give me 42 plus y is equal to 180. I'm going to move the 42 to the other side, and I think that's going to be 138 degrees. But now that's just y. That's not x. So now if we go back to the picture, the reason why this was helpful was x and y are supplementary. So I'm going to say my reason here is supplementary. And I'm going to go ahead and say, okay, x plus y is equal to 180. Plug in the 138 that you found for y, and then solve for x. And you're going to get 42 degrees. So that's one way to do this. There's another way to do it, though. And it's all about looking for patterns inside what we just did. So we figured out that x was equal to 42 degrees. But if you take a look at the other set of work, this whole triangle sum business, the 42 degrees already showed up. It showed up back here when you added the 19 and the 23. So if we take a look back at the picture, if I want to figure out what that angle x is, what I can do is I can actually look inside the triangle. Got to be very careful about this. And you are going to use the remote interior angles, which means you're going to find the two angles inside the triangle that are not butted up against the x. So it can't be the corner that's right next to it. It's got to be the other two corners that you can add together. So another way to do this, if you see the pattern, if you don't worry about it. You can still get it this way. We can do, and I'll leave a little bit of space so we can write down the formula or the name of the theorem for this. We can take 19 plus 23, and that's going to be equal to x. So x is still going to give us 42 degrees. And this is called exterior angle theorem. So you have to make sure, so we'll do a little drawing of this guy down here in the bottom so we know really what it looks like. You're going to have a triangle. So we take any triangle here. We're going to go ahead and draw it. Doesn't really matter what it looks like, just as long as it's a triangle. In order to use the exterior angle theorem, you need to make sure that one of the side lengths is a direct extension of itself already. So you can't have a random side length coming out like that. That's not an extension of one of the other sides. You have to make sure that it is a direct extension of the side that already exists. So that could be one of them. Or you could have an extension of the other side length. So it has to be a direct extension so that the angle that you would be looking for is right there. So it is exterior to the triangle. Or you could also take this other side and you could extend it in either direction. But you got to play by those rules. So if this is the example that we're going to use and say this is x that we're trying to find, the two angles, so those remote interior angles, not next to x, go back inside the triangle, and you're going to find the two angles that are not next to x. And what we would do is we would add those together. So if we call that A and B. So this would be the exterior angle, gives us A plus B. That's your exterior angle theorem. Now, you're also welcome to use triangle sum and supplementary. That will suffice as well. Okay, and then triangle inequality. So this is also in the notes. This is going to be page 9. This has to do with the side lengths themselves. So here was another way to take a look at it. So we could go ahead and say, well, instead of each one being the sum of each side, if you're less than the sum of the two sides, then you can go ahead and manipulate it and actually get this representation as well. So I am going to go ahead and pause, get this one filled in on the end so we can figure out, well, what is acceptable for the third side length. And then I think we are either done or super close to being finished. Okay, so I went through, I took the two side lengths, I added them together, knew that the missing side is going to have to be smaller than that. But then I took the other two side lengths, I subtracted them. Make sure that you subtract it so it makes sense. It doesn't make any sense to think about -2 as a side length. So we do want it to be the +2 aspect. So you could write it as those being your options, or you can go ahead and write it as a compound inequality, in that your measurement B is going to be in between a minimum length is going to be a little bit bigger than 2, and the maximum length being a little bit smaller than 14. So you can actually write it that way as well. And that finishes up these notes.